Okay, here we go. Second video, third lesson. I'm going to try to make this shorter as per Mr. Zatur's advice for me. So I have some, you'll see as I go through there, I have some things that are highlighted in yellow. Those are things I've already decided are going to be in the kind of warm-up targeted practice that we do in class on the following day. So if you're scrolling through the video and you're like, when is he going to explain that thing in yellow? I'm not going to explain that thing in yellow. That's an example that's saved for class. So what I've got left in here is we're at least going to go through all of the basic concepts at least once. So if you're absent, like this video still covers everything. I'm just not doing all the examples because I want to keep the video short. Okay, so this one is about translations, rotations. It's another combined one of geometry and algebra 2. So let's get to it. So the translation is the one that just kind of slides things. And you see all these little vectors, all these little connections are kind of going this way. A translation, the nickname for translation is just a slide. So it's a very simple transformation. It's like you're taking, it's like you're copy pasting something and just kind of shoving some figure or some point or some geometric figure in a certain direction by a certain distance. And when you define a translation, you kind of say like, well, what is the specific translation you want me to do? You have to give it a vector. You remember watching Despicable Me? There was a character named Vector. He had direction and magnitude. That's exactly what this is about. All these vectors over here, that you notice they all have the same, they're kind of taking the same trip. They're all going 3 units to the right and 1 unit up, kind of. They're all taking this same exact vacation when they go from B to B prime or A to A prime or B or C to C prime. This is how you write these vectors. Notice if you zoom way in here, you can see this font, or this notation. It looks like kind of like that on top. It's kind of like a array notation, but it only has one fin on it. And you can read all this. I'm just trying to get through it quicker. The notation for vector is that. This is the notation for the magnitude of the vector. They use these absolute value bars to kind of talk about it. We're just talking about the positive length of it. We're not going to spend a lot of that. Doesn't come up a lot, actually. We don't mention it very often. And you can find the length of the vector pretty quickly with Pythagorean theorem. If I wanted to find the vector, the length of this thing, it would be pretty quick to do. Okay. So we can define a vector by saying, well, I want to use the vector A prime. You can also define a vector by using coordinates. Now here's another notation that uses 2 numbers in the comma. Those brackets are fun, aren't they? Yeah, they're pointy brackets like that. Those brackets in geometry are reserved for vectors. It's the vector, when you write AB like that, it's basically where the point AB, what does it say here? A represents the horizontal change and B represents the vertical change. Basically, AB is like where, it's like the coordinates of the point where it would move 0, 0. We'll have some examples of this later. It's basically, we need to add A to the X coordinate and add B to the Y coordinate, like it says here. Okay, and a translation is another one of those 4 isometries. The first one we did last time was reflection, and today we're doing translation rotations. That's going to be 3 of the 4. All right, so let's actually do this one here. So they're saying, here's a translation, and again, we're going to do these other ones later. We're going to do B and C. So just to take the PQR to the P prime, Q prime, R prime, that's taking this one here. What is it says find the translation vector. So they gave us the pre-image and the image. They're saying name this vector, or give the translation vector. So it took this translation took P to P prime, like that. It also took R to R prime. This is an equivalent vector. It also took Q to Q prime. All these vectors describe the same motion. They are equivalent. I've drawn them in different places, but yeah, they mean do the same translation. So all those vectors, what's kind of cool about this, I think I could take this and move it. Can I just move this around? Oh, no, I can't. This vector, and again, they're all the same. This vector, you could think about this, or you could kind of measure it by looking at how far it went left and right and how far it went up. Its horizontal component is it went this way 8, and it went this way 2. It would take the point, this is what I was saying before about the vector notation. It would take the point 0, 0 to 8, 2. Right, 8, 2. So one way to name this vector is to name it the vector 8, 2 with those kinds of things. Now that's the name of the vector by itself. The translation notation, did I talk about this? We used capital T and then a subscript. Okay, or here they did T with a colon. I'm sure we'll see it later in the worksheet. We will do the other 2 vectors in class. That'll be the one things we start out with. Some translation T takes point 2, -5 to the point 1, negative 6. Where's the translation vector? Okay, so I have to draw this. 2, negative 5 is here. There's the point A. It takes the point to 1, negative 6. Oh gosh, 1, oh, I didn't go negative 1. 1, negative 6. 2, negative 5. 2, negative 5 to 1, negative 6. It just went there, right? It went over 1 and back and down 1. Each of these things are kind of like 1. So it went left, right, it went left 1, and it went down 1. I believe that is the vector notation we're talking about. That's the answer to this. Translation vector is negative 1, negative 1. You can also see that because that's what happened to these coordinates in terms of adding and subtracting. I took the x-coordinate minus 1, and I took the y-coordinate minus 1, so that's the translation vector. We'll do the rest of that in class. I don't think those are central concepts, honestly, the B and the C, or at least those are things that if you say you missed class but you saw the video, you could still piece that together. This little paragraph I reprinted here for your reference, and we've talked about that before. Now let's move into algebra 2. So we are talking about doing translations in algebraic functions, like coding, kind of like we had to do in the last lesson where we talked about reflections, the things like f of negative x and negative f of x and that kind of stuff. This little type of format of taking a function and then adding or subtracting something to it, that's going to, I mean, spoiler alert, that's going to give us, guess what, a translation. So translations in excuse me, algebra come from, one of the ways we can get a translation in algebra is add or subtract some number to the end of the function. So this little squiggle, they do this a lot. This is kind of abstract. What the question is, describing words, how you could transform the f of x into the kind of the purpley thing here. Because what they're saying here is there's this weird, and we've seen this little squiggly guy before. That's the original f of x. If you were to take f of x and add 4, and maybe you can imagine this in a algebraic, like numerical sense. If you had coordinates for this coordinate, we do have, we can see this is 2, 3, and it moved up here to 2, 7. Like all of the points just had 4 added to their y coordinates. So, and now that we know the geometry term for this is a translation by 4 up, is what happened in words. So notice what happened there. I'll let you guess for now, but we will do this in class to solidify that learning. What's going to happen if you subtract 3? Anyway, if you add 4 at the end, like outside at the end of the equation, just take whatever f of x you have and add 4 at the end. That's going to take the whole thing and just shift it up by 4. What happens if we were to add or subtract some number before we apply f? So notice how this plus k business here, this plus k business here was on the outside of f of x. It was f of x and then add k. This was f of x plus h, or minus h, inside the parentheses before we apply f to it. Okay, so this is a little bit different. And if we do examples of actual algebraic functions, you can see how the inside and outside adders, like the h and the k, would kind of operate differently. So describe in words what's going on here. This is f of x. This is f of x plus 3. Yes, it is f of x plus 3. This is not a typo. What happened here? Well, you should see everything kind of went like this. Everything went like this. Here's this coordinate again, 2, 3, and where the corresponding coordinate in the graph at this point is, notice it's negative 1, 3. Yeah, so we actually do have, if you can imagine why this says plus here and why it went the way that it went. This, I know that, let me draw this here. I know that if x is 2, f of x is 3. So if I'm going to try to make a table for the function of f of x plus 3, I have to think about what x plus 3 is before I try to find f of x plus 3. So if I put negative 1 in for x here, I'm actually operating on 2, and I know what f of 2 is. F of 2 is 3. That's why this point shows up on the graph. Rewind that and watch that again if you want to hear that explained again. This is a translation again by 3 to the left, and you might be surprised by that plus 3 made it go left, but it really did, and this is an explanation of why, which you will hear me say several more times in class, because it is surprising. That's why this question's here. Did you expect that to happen? Maybe you didn't, because up here, plus was up, and guess what minus is going to mean? But plus is up. Here, plus is left. You might have expected plus to be right. But again, there's an explanation of why plus is actually left. Okay, next, describe how this is transformed. Okay, and let's try to actually write the equation here. So what happened from f to g? Well, it looks like it kind of did some kind of trip like this, and that's exactly what happened. We have a vector here. We can imagine what happened like that. The vector looks like it went over 2 this way, and it went up by, what is that, 5? 1, 2, 3, 4. Yeah, looks like it went up by 5. It's kind of like translation by vector, and this is actually how you do this. We haven't seen this yet, but this is what I was talking about earlier. Translation by 2, 5, the geometric notation for that is this. T for translation, subscript with the vector. Anyway, I know that this thing went 2 right, and 5 up. So what happens with the 2 right? The right and left we just talked about. I need some more room. Let me move this around a bit. We went 2 right, and 2 right would take an f of x function and do this to it. If you believe, this thing we just did, right? This is the 3 left. 2 right would do that. The 5 up is like this type of coding, right? So we have to do all of these things at one time to get from f of x to g of x. We could say g of x equals, and then we got to do all of this to f of x. We have to add, or we have to subtract that 2 on the inside, and we have to add this 5 on the outside. That's going to produce a translation of 2, 5 the way we want it. Okay, we'll do this one in class. See how this works? See, I'm kind of almost done, and we're moving right along here. We're at rotations already. Rotations is the act of kind of turning something. I think rotation's a pretty good name for it. This is a little more complicated than translations. The definition of rotation is an isometry, just like reflections and translations. But rotations are defined and they're specified, and they're kind of they're communicated as you need to not only talk about the angle of rotation, like the amount of turning that has to happen in degrees, but you also have to talk about the center point. It makes a huge difference where you pin down the paper as you spin it. Yeah, so there's that. So it's defined as if you're spinning the point around the origin, of course, or around the center of rotation, it doesn't move, but everything else moves through an angle, and there's a picture on the next page, moves through the angle that's defined. The other thing that's a little weird about this is counterclockwise is defined to be positive, and clockwise is defined to be negative. This will make a lot more sense when you get into calculus, or you get into actually pre-calc and Excel 2 next year. I'm talking about the quadrants and the coordinate system, like as we know it. That leads to this actually, quite clearly. But for right now, you're like, what? The clock is backwards? Yeah, the clock is backwards. Okay. So here's the notation. We use a funky font on our R. We use kind of a curly R because we had R for reflections. We use this kind of R. Now, when I draw it, I don't draw it with those kind of corners in it. I just kind of make an R that looks curly, kind of like that. Curly for rotation, I think makes sense. And then in the subscript, we have a subscript for the center and then for the magnitude. So this is around 0.0 negative 90 degrees. Yeah. This part's kind of silly about how we could rotate more than 300 degrees or 360 degrees, and it would just keep, you could define a rotation like this if you really wanted to, but it's kind of redundant to do that. There's a special rotation called a half turn that's 180 degrees. So this is a rotate. We've talked about this a little bit in algebra. If I rotated point P 180 degrees around point O, it would go there, and R 180 degrees about around point O, it would go there. Sorry, it starts here, doesn't it? And it kind of, with 180, it kind of doesn't matter which direction you're going, because if you go clockwise or counterclockwise, you're going to end up in the same place. It's got a special name of half turn because it has special applications in further transformational geometry. What's really nice is you can perform a half turn with a ruler. You don't need a protractor or anything to do fancy rotations. We're not going to do rotations with protractors anyway. You're going to be more describing rotations after you've seen them printed rather than trying to do rotations by hand with a protractor. It's really tedious. Performing rotations of 90-degree multiples on graph paper is really not that bad. So that's what we're gonna spend our time doing first. Okay, and yeah, half turn has a special notation of just h. Okay, let me do a couple of these examples. Diagonals of this square intersect at point O, complete each statement. Okay, if we rotate B, so B is the preimage. We're rotating B using center O. This is going to start rotating around center O. how many degrees? 90 degrees, and that is clockwise 90 degrees. If we go clockwise 90 degrees from where B starts out, it's going to end up at D. Similarly, I'm doing all these. I thought this was important enough to do. If we center our rotation at O, I'm on B now, and we look at point A, and we're looking at rotating point A somewhere around like centered at O, it's going to move around that circle. If it goes 180 degrees around around a circle centered at O, it's going to end up at D. Also, next one, centering at point O, we take point C and we rotate it around this circle 270 degrees. 270 degrees, but that's counterclockwise. That's this way. 270 degrees counterclockwise is going to take us to D. Gosh, did I do that right? Are they all D? I hope I did that right. I really hate making mistakes on this thing. Yeah, I'm sorry, that's not counterclockwise. Counterclockwise would be, the clock goes that way. Counterclockwise would be that way, right? So this would be A. Ooh, that was close. I almost had a mistake on that thing. Okay, yeah. Name 2 rotations that take C to D. Well, one of them would be, I could go from C to D if I centered it at O. I think, let's just have them centered at O because it'll be easier. Centered at O. I could go that way or I could go that way. This one is the counterclockwise one, so that would be positive 90, or I could do negative 270. It would take me to the same place. Okay, this next one with the graph paper. Rotating about point A, which is the origin, which most of the time when you're rotating things on on graph paper, you're going to center yourselves at the origin. Rotate 90 degrees. We'll do the counterclockwise one in class, but rotate this counterclockwise 90 degrees. Counterclockwise is going to be that way. We're going to go 90 degrees that way. Well, A isn't going to go anywhere, so that's just going to be A prime. C counterclockwise. Okay, this isn't so bad. Right now, it's almost like you could think about C being at the end of a clock hand or something like that. That's centered at point A, and it reaches out kind of 5 units to the right. When I rotate that thing 90 degrees, it's just going to go right here. That shouldn't be too hard to imagine. What's hard to imagine is where B ends up. B is the same thing. B, let me change color here. B is at the end of a clock hand that's centered at A, and it's got to rotate around this clock, and it's got to go exactly 90 degrees. How on earth do I recognize exactly 90 degrees? This is easier to see if you can see me moving my hands around, but yeah, to make sure this is going to be exactly 90 degrees, I think of this. So this is 5, and this little height here is 6. I think instead of thinking about this clock hand, that green thing there, I think about kind of an L-shaped arm that's holding B out there from A, and it's an L-shaped arm that goes like this. It's an L-shaped arm, or it's like the 2 sides of a rectangle or something that are 5 by 6. And when I rotate that 5 by 6, well, let's make it just dark green just for fun. It's going to rotate, and now the 5 is going to come up this way where it was for C, and the 6 is going to go 6 out this way. So that whole L-shaped thing is going to kind of now rotate, and it's going to tell us exactly now here is where B prime goes. And so, yeah, that's where that is. The final triangle is here. So there's the, I don't know if you can see this purple thing or not, but there's the final triangle, A prime, B prime, C prime is right there. Okay, we'll do the other one in class, and you'll see, again, you see me use my arms. I think it's a little easier. What if we had to rotate point P? You know what? I've just decided, because the video, I'm watching the time, this seems kind of long. I want to do that one in class. All right. This last one I do want to show on video because you might want to watch this over and over again. The paragraph explains it up here, but basically what we want to do is locate. So they're going to give you this thing that has been rotated somehow. Maybe it went that way. Maybe it went that way. We don't know, but they're just saying find the center of rotation. So what we were going to do with because of what this paragraph says about how if anything rotates, it kind of reminds me of this. As I rotate anything around and think about its image and preimage, that image and preimage are on the same circle. And if it's on the same circle, if it's equidistant, like they're both equidistant from O. If we think about all the points where the center could possibly be, if we didn't know where the center was, it has to be equidistant from the image and preimage. It would have to be along the perpendicular bisector of the segment connecting the image and preimage. So what I mean by that, or what you're going to have to do, and you can do this with a ruler, this is a sketch, this isn't a technical drawing. I'll pick 2 points, like Oh, f and f prime, because they're nice and close together. I'll pick f and f prime, and I'm not doing this with a ruler because I'm on an iPad. I'll show you on the board with an actual ruler. And I make the perpendicular bisector of f prime, which is going to look like something about like that. That looks like the perpendicular bisector of f prime. I know any rotation that takes point f and rotates any number of degrees and lands me on f prime, like maybe say that point. This segment, ooh, that's really bad, is going to be congruent to this segment. So that's a possible center of rotation. Any point on the line is really kind of like all possible centers of rotation have to be on there. Could be this point. That's a center of rotation that could take f to f prime. This point way out here could take f to f prime. Anyway, this line here is the set of all possible locations for a center that could be a place that could be a center of rotation for those f's to go to those f primes. Then I need to pick another one. How about B? I'll change color. Let's do B. So B from here to here, the center of rotation, any center of rotation that takes B to B prime has to be on that perpendicular bisector. So something like this. Perpendicular bisector, this is all blue, it's a lot of overlap. So guess where the center of rotation is for the whole darn picture? It has to be here. This is the center of rotation. It's the place that's the only point that could be a center of rotation for B and F, so it has to be that one. Okay, we will do lots more of these in class. Those are kind of hard. I don't want to go over this really ever, but there it is. If you want to try, if you're one of those people who likes to memorize formulas, go ahead and memorize these. They're all here for you. And I believe that's it. The next thing's homework. I'm going to stop now. Thanks. See you in class.